This is the last video in my metaprogramming series, and I wanted to cover a variety of notes that haven't come up yet in the previous videos that I think are very important for learning how to write good tactics. First of all, I have to discuss interactive parsing, a very fundamental piece for writing tactics that you can actually use. I wanted to talk about pattern matching in the tactic monad, because that hasn't come up yet. I wanted to talk about goal management and meta variables. And finally, I wanted to talk about interacting with the environment directly and writing user commands, which are a non-tactic form of metaprograms. All of the tactics that we've written so far haven't actually taken any arguments from the user, but usually if you write something like apply or exact, you provide the tactic with the proof term that you want to use. In what we've done so far, well, we'd have to write those proof terms with this backtick expression quoting, which is not the most convenient and certainly not how we normally apply tactics. So the key to doing that in the proper way is interactive parsing. So as an example, I want to write a tactic where we take a natural number and we add a proof to the context that that natural number is non-negative. So before we get into the interactive parsing part of this, let's implement the tactic that does what you want. And that one's simple enough. Let's call it add non-neg proof. And this is going to be an aux function. So I'm going to take in an expression that represents the natural number that we want to deal with. And I want to take an optional name. So we don't have to provide a name for our proof if we don't want to, but we can. Type tactic unit. And this is straightforward. We've done something similar already. Let's make an application of the function nat.0le. I can give it the argument n, so this should be a proof that n is greater than or equal to 0. Let's get an unused name. I don't care for now if it's pretty or not. And then we're going to note. So if we provide this optional name, we should use that. Otherwise, we can use the name we just generated. We can write that as h.get or else, which is a useful function if you're dealing with option types. We don't need to give the type of what we're adding to the context. We just need to give the proof. And we can finish with skip to make it type check. OK, that's a straightforward enough. But if I wanted to actually apply this, let's write an example down here. It's kind of inconvenient. You can say begin and add non-neg proof aux. Then what do we have to say? Well, the n plus n, none. But it says unknown identifier n, so we need to do something with the name resolution. That's kind of awkward. And maybe even if we don't put in that, we'll put in n, let's just give it a natural number. OK, there's a proof that 55 is non-negative, but I still had to back quote it. And normally when I were in a begin end block, I wouldn't have to write these funny backticks. So obviously we're missing something. What we're missing is the interactive version of add non-neg proof. So I'm going to enter a namespace. We're always going to work in the namespace tactic.interactive when we're writing things that parse like interactive tactics. And there's a command that's implemented in mathlib that's called setup tactic parser that just opens some namespace and adds some local notation for us. This is also very helpful. And so what I'm going to do in this namespace is define a slight variant of add non-neg proof. That takes roughly the same arguments that our version up here took, but in using some different types. So first of all, let's take the name first. And then let's take the natural number. So what is this parse that I've written? Well, interactive.parse, in some sense it's sugar, but what it's telling Lean is that when you're in an interactive tactic mode between begin and end, you should try to parse some identifier. This has type parser name. Parser is a monad. We don't need to go into that. But this is somehow going to produce a name. Parser.pexpr will produce, as you might guess, a pre-expression. So that's an unelaborated expression. And if you think about it a bit, that makes sense. If I wrote n plus n, well, that's not a full expression on its own yet. I need to do some extra work to elaborate it, to figure out what plus we're talking about, whether that all makes sense. So in interactive mode, we don't really write expressions. We write pre-expressions. So I tell Lean to parse a name, to parse the pre-expression, and then we have to do something with those things that are parsed. So we were going to end up calling our original function in the end, but that took an expression. So we need to elaborate the pre-expression we gave it. We have a function for that. To_expr took in a pre-expression and elaborated it. So let's do that. And then conveniently, that parse ident, that's actually definitionally equal to just a name on its own. So I can just write this. This parse ident reduces to a name, and actually we took an option name up here. Lean is coercing the name that we give here into an option name. The reason that I wrote option name is because really I'd like to avoid giving this name argument sometimes. In fact, I'm going to move this to come after n instead of before. But I'd like to have the option of not providing a name for my new proof and let Lean figure out on its own. So if I put a question mark after ident, the question mark is just notation for optional, which makes this into an option name instead of a name, which means that I don't have to provide it in my interactive proof if I don't want to. So let's see what happened down here. Add non-neg proof. Instead of writing the back-quoted 55, I should just be able to write 55. And there's my anonymous thing, _x, which is a proof of what we thought. And if I want, I can call it hx. So that's pretty cool. But now I want to do more. Instead of just adding one non-negative proof, what if I give it a list? Or, well, I can even check for now. What if I give this n plus n? Okay, we're still good there. But what if I gave it a list of expressions? Let's write a new variant of this. Add non-neg proofs. So this, instead of parsing a single p-expr, we want to parse a list of p-exprs. So there's a parser called p-expr list, which produces a list of p-exprs. I'm not going to take a list of names for them. I'm just going to do them all anonymously. So, okay, I got a list of p-exprs. I want to elaborate all of them. So I need to map to_expr over all of these p-exprs. Do that using mmap. So now I have a list of expressions, and for each expression, I want to add it, or add the corresponding non-negative proof. So I can do I can do L dot mmap primed, since now I'm doing a tactic unit, add non-neg proof ox. Except because there's an option, let's say fun E none. And then it's happy. Let's try to add a bunch of things down here. That is, let's try to add proofs or a whole bunch of natural numbers. Yeah, so there we go. For every p-expr that we put in this list, we probably don't even need these parentheses, we add a proof of non-negativity to the context. So as a general rule, anything that you write that's intended for interactive use should be in this tactic.interactive namespace. Even if you're not parsing any arguments like we are here, it's it's good style. It simplifies things overall. How do you parse these arguments? We saw a few. We saw ident, we saw the question mark, we saw p-expr and list p-expr. But if you jump to some of these definitions in this file parser.lean, you see a whole bunch of other options that are implemented. So you can see all kinds of different things that you can parse. If you look at tactics that you know and you want to kind of do the same kind of parsing, you can look at the parsers that are implemented for those and try to copy them. The next topic is a quick one, but it's going to come up in the next example, and we haven't talked about it before yet. I wanted to mention pattern matching in the tactic monad. So let's suppose that I have a function of type tactic list n. Call it make list tactic list of natural numbers, and I don't really care what it does for this example, so let's just say return the list 1, 4, 6. Now, in another tactic, I might want to call makeList and get the result. And maybe at that point, I know that makeList is going to return a list with exactly 3 elements. I'll do this as a run command instead of implementing another tactic. So I could do something like this. Let's say L gets makeList and trace L. It prints exactly what we'd expect. But what if I only want the first element of that list? I could say match L with something, then trace H, otherwise fail. And okay, that works. What if I wanted the second element of the list? Well, the pattern match gets a little more complicated. So this can get harder and harder, more and more awkward to split on the result of a tactic like this. So here's a nice shorthand for doing this kind of pattern matching. I'm going to just write a 3-element list, A, B, C, and I'm going to bind the result of makeList to that. And it prints what we expect. B, the second element, is 4. So this is basically combined a call to this tactic makeList with a pattern match. What if I got my pattern wrong? What if I told it I'm expecting 4 elements and only gave 3? Well, the tactic fails. It says, as we might expect, the match failed. I didn't actually give it I didn't actually produce a 4-element list. So this is a short tip, but in practice, you find yourself writing tactics that do this very often. And in fact, we'll see it in the next example that we do. So one thing we haven't talked about much yet is metavariables. Another thing we haven't talked about much are tactic states that have multiple goals. And these two things actually kind of go together. So in a proof state, sometimes we have more than one goal. There's the first goal that we're working on at the moment, but there are other things printed below it. It turns out that in any proof state with 0, 1, or more goals, each goal is represented by a metavariable. A metavariable is like a placeholder. It's an expression that didn't have a value yet. It did have a type, but maybe the type of the metavariable could be another metavariable. And so this is actually a very convenient way to represent a goal. A goal is a term whose type we probably know, whose body we don't know, that's waiting to be filled in. So we can actually access the goals in any proof state using a tactic called getGoals. So let's set up a proof state that will actually have multiple goals. Let's say I'm going to prove true and true. So I'm going to split let's get the current goals, and let's map them. We see that our goals are two metavariables, M1 and M1. The printing is actually kind of inconvenient. They're not the same metavariable, but each one is the first metavariable in that particular context. Let's print something a little more interesting. The types of those metavariables. And okay, that makes sense. They're both true in this case. Maybe we're trying to prove true and false. And then we see one is true, one is false. Let's see another thing that we can print instead of their types. Let's trace the raw format of these expressions. What do metavariables really look like? Well, they have a name, pretty printing name, a type. They have some information about them that's stored in the expression format. So how do metavariables end up getting assigned and replaced? Well, one way, if the metavariable is representing a goal, then what tactics like exact or apply are doing, they're assigning those metavariables representing the first goal to be instantiated in some way. In the case of something like apply, where we often get left with more goals afterwards, it creates some new variables to represent the new goals and instantiates the original metavariable to the application of some constant to those new metavariables. There's a part of the tactic state that we usually don't really look at explicitly. It's called the type context that manages these metavariable assignments. If I have a metavariable and the type context knows that it's been instantiated to something, then it's possible for me to replace that metavariable expression with the thing that it's been instantiated to. But that doesn't happen automatically, and this can sometimes be a cause of confusion to people who are writing tactics. So to show you what I mean here, let's do another quick example. I'm going to prove there exists some natural number x such that x is equal to x. So how do we prove this? Well, one way is to apply exist.intro. Apply C is a convenient tactic that takes in a name and applies that name, or applies the declaration with that name. What should my goal state look like here? Well, I'm waiting for a proof of x equals x, but I'm also waiting to know what x actually is. I haven't told it what I'm using to instantiate this. So I know I should have two goals. Let's get them. What's the output here? Well, OK, I have two goals. They're metavariables. What are their types? Here's another useful monadic way of writing things that you might find handy. I'm inferring the type of E1 and immediately piping it into trace instead of assigning it to its own variable. So this is binding two monadic functions together. It's just faster than writing it another way. We see that, OK, the type of E1 is something equals something else. That something is actually the thing that will be a nat. It's actually the second metavariable. And after a few more traces, just to see exactly what's going on. So yes, so they're both metavariables, as we might expect. So now let's try to make an assignment. I want to tell Lean, OK, set this actually, let's try to set this second thing, this metavariable whose type is nat. Let's try to assign that to some value. I'm going to erase my tracing. So the unify tactic takes two expressions, and it tries to assign metavariables in a way that will make those two expressions equal to each other. So let's try to do this. Let's try to do unify E2. And we need to pick a natural number. Let's say 7. And let's trace E2. Hey, Lean tells me E2 is 7. Cool. But this is actually misleading. Remember, the raw format of E2 before was just some metavariable. What's the raw format of E2 now? It's the same metavariable it was before. Even though when we trace the pretty printed version, it says 7. So what's going on there? Well, when Lean pretty prints metavariables that have been assigned in the type context, it actually prints them as if they've been replaced by their value, even when the raw expression is actually still a metavariable. We can tell Lean to stop doing this. Instantiate. If we set instantiate metavars to be false, then, OK, good. Lean prints this as a metavariable instead of its instantiated form. But maybe we've written another tactic that we want to give the expression E2 to, and we want that expression to know the assigned form of E2 instead of the metavariable. Maybe it cases on the expression structure of the input, and we want it to be an actual natural number, not a metavariable that's been assigned to a natural number. So there's another tactic here called instantiate mvars. And now if we instantiate the metavariables in E2 and trace the raw format, now it looks like a numeral. Maybe you don't recognize this as a numeral immediately, but I promise it's actually a numeral. So if you're dealing with goals and metavariables and unification directly in your metaprograms, this kind of thing can come up. You should be careful about what's an instantiated metavariable, what's an uninstantiated metavariable, and what's a raw expression. If you're not dealing with goals and unification directly, you may never see this. Every once in a while, you may see it as a bug from another tactic that should instantiate some metavariables that it assigns but forgets to. This set option is a useful way to debug things if you see weird behavior that could be related to this.